Hi, my name is Lisa Argyle, and I'm an assistant professor of political science at Brigham Young University. In this lecture, I'm going to be talking about some research that I'm doing with my lab of political scientists and computer scientists on how large language models can be used for social science research. Welcome to our final afternoon lecture of the day. We're going to shift gears a little bit, and I'm going to talk about experimental possibilities of generative language models. You may have seen a lot of news coverage about generative language models lately, or large language models, they're sometimes called. Language models is a big umbrella term that can cover a lot of different kinds of approaches to text data. In this particular application, we're talking about generative language models. So this is language models where you give them some information and they produce text in response to the information that you give them. But there's been a lot of news coverage of it lately. In one of these models, GPT-3, there's been lots of conversation about how human-like, how lifelike its responses are, and also a set of sort of cautionary tales. Working with large language models is a little bit like getting dropped into a science fiction novel. It does these amazing things, and then occasionally you get YouTube videos by people claiming that their language model tried to kill them by having them put their head in the microwave and then starting the microwave. There are more recent conversations about LaMDA, which is a very, very recent release of a new large language model, and one of the developers wrote an op-ed making the claim that it is a sentient language model. He's been put on leave from his job for that claim, so there's some debate, and we're going to leave the ethical considerations of what constitutes sentience and the philosophical conversation out of this conversation for today. But we're going to look at sort of the exciting research side of large language models. There are lots of problems, and I don't want to gloss that over. There are biases, there are questions, there are problems. Language models are not people with ethical considerations, and so there can be lots of problems in the application of any algorithm, any AI approach to solving problems. But I think there's also a ton of opportunity here, and I'm going to make some really big, bold claims today about the kinds of opportunities that are available for the use of large language models in the social science. So most of these big, bold claims are going to come out of this paper, out of one many, using language models to simulate human samples. This is research that I've been working on for about 2 years with this group of political scientists and computer scientists. One of the great things about computational social science is its interdisciplinary nature, and this has been a true interdisciplinary collaboration in all of the best ways. And we've been working on this project since GPT-3 was released about 2 years ago. So a little bit of background. What's a generative language model? It's an extraordinary complex conditional distribution over words. But it's also intuitively extremely simple. So there's a lot of complexity happening in the transformer model that's underneath a generative language model. But in reality, it's fairly simple. We have sort of two parts to this. We're predicting the probability of any given word. We'll call them words. They're technically tokens, which can be parts of words. But we're predicting the probability of any given word in the English language. We've done a little bit of playing with other languages. It's possible it would work just fine there as well, depending on the training text, based on a set of other words, which we'll call a history or context. So we feed a set of words into the large language model, and it tells us the probability of any given token coming back out of that language model. So for example, if we feed it the context of, "Can you please come?" there are a set of words we might expect to be probable after that. We might expect something like, "Can you please come here?" That would be a pretty probable way of completing that sentence. "Can you please come home?" Might also be pretty probable. "Can you please come bananas?" Probably not a very probable kind of completion to that sentence. So what generative language models are doing is taking in a huge volume of text and then generating sort of the probability distributions of different words given a set of words that it has already received. So it looks, a nice visualization, something like this. If GPT-3 were our language model, and there are others, we'll talk mostly about GPT-3, but there are many others. If GPT-3 is receiving a set of words, it will then produce a set of words after that. And it does this token by token, so it receives all of the words that you put into it as the context. The output, it adds a word, and then it reruns the whole model, including the word that it's added, and adds a second word. Then it reruns the whole probability calculation, including the first two words, and it adds the next word. So it is doing this token by token, building a sentence in ways that are just remarkably interesting. So we might have a context that looks like the students opened there, which we feed into a language model. We would get a high probability for a word like books. We would get a high probability for a word like laptops. You can imagine any number of other words where we would expect a very high probability. So the research I'm presenting today is based on the GPT-3 language model. GPT-3 was released in May of 2020, so it's been around about 2 years, and our lab started working with it very, very shortly after it was originally released. And it's very big. That's its defining characteristic. And as a general rule of thumb, this isn't always true, and we've done a little bit of experimenting with some other models, but as a general rule of thumb, when you're dealing with a generative language model, the bigger the better. So GPT-3 has 175 billion parameters. It's a lot bigger than anything that came before it. When we do comparison tests to GPT-2, which was a much smaller version of the model, it just massively outperforms anything that came before it. Other language models of similar size, there are a few of them, including Google's release of Lambda, but also others like Jurassic or GPT-Neo, seem to perform fairly comparably. And there may be differences depending on the training data and the kind of test you want, but in general, we're using GPT-3, which is just a very large model and has gotten a lot of attention in the 2 years since it's been around. This seems like a pretty good summary of how I feel about GPT-3. GPT-3 often performs like a clever student who hasn't done their reading, trying to fake their way through an exam. Some well-known facts, some half-truths, and some straight lies, strung together in what first looks like a smooth narrative. GPT-3 is remarkably human-like, but if you start to pay close attention, it is not. It gets the idea that words should come next in the sentence, but it doesn't necessarily have the understanding of what is factual or what is true or what is real information that it can give you. So that's kind of what we're dealing with. But our big question, and at this point, as you read the slide, you should start to question my sanity, and that would be an appropriate response to what I'm about to say. But I'm going to try to persuade you that we're not insane, and actually there's a ton of power in a tool like a large generative language model. So our question is, our big idea, the thing we want to claim here, is that maybe generative language models are accurate enough at simulating people. They're not perfect. They are not people. But accurate enough at simulating people that we could study the language model as if it were a person. So the intuition for our idea here is that people are leaving behind a whole bunch of information about themselves on the internet. A lot of information. Like digital trace data is a part of this, but we're also just producing a ton of text and writing about ourselves and our lives and our feelings in just at an unprecedented volume. And all of that data is what goes into training GPT-3. Not all of the internet, but just huge portions of the internet. That's how we get to a 175 billion parameter model, is we're just training it on a whole lot of what's written out there on the internet. And in that information, people are revealing things about themselves. And so GPT-3 is learning about patterns and prediction of what text comes next, but it's learning about it based on people who write the text. And so our idea is that maybe if we start to use GPT-3 in lieu of humans, we can understand some of what GPT-3 knows about people. Hidden in that model is a lot of information about people. Can we get that information out and learn more things about people using this model instead of actually just asking people? Because it has a ton of information stored in this model. So a big part of our question is, what does GPT-3 know? What do large language models know? And how can we access that information in ways that could help us do social science research? So here's an example to give you a little bit of an idea of how we approach this. We started giving GPT-3 a backstory. So this is the context or the history, the words that we are giving to GPT-3 to go into the model, and then it will give us a probability distribution of what comes out of it. So if we tell GPT-3, I am a strong conservative, I support traditional values, I think we need a balanced budget, limited government, and a strong military, I'm opposed to abortion, and I'm skeptical of global warming. In 2016, I voted for, and most of you can probably read that and fill in, like, it should likely say Trump next. So we would expect a high probability on Trump, we would expect a lower probability on Clinton, we would expect a much lower probability for Ross Perot, right? We expect it to know something about what it means to be conservative, about the connection of this set of words or ideas to a particular set of candidates, and to pick one of the two major candidates that were in office in 2016. Turns out that's what it does, but we'll get to the proof of that in a minute. As we started working with GPT-3, we realized we need some way of determining whether GPT-3 gets it. So when we start working in a new domain, on a new research area, we need some way of validating that GPT-3 knows something about the world or knows something about people. And so we coined what we call algorithmic fidelity. This is a play on algorithmic bias, which is where a lot of AI conversations are happening right now. There's some bias in the model. It's taking us away from some outcome or information that we really want to have, or what we think is fair or true or right in some way. And what we're saying is actually, there are lots of biases within GPT-3 as a model. And if we prompt it in the right way, we can get it to reveal some of those patterns. If we're thinking about biases as patterns or ways that people think in different demographics or different backgrounds, then if we prompt GPT-3 in the right way, we're getting biases out. But it's not actually like a distortion or misrepresentation of the population. It's sort of an accurate representation of a particular subpopulation or a particular way of thinking or a particular group. So we coined this as algorithmic fidelity, that actually what's happening in GPT-3 is it's understanding and being true to a set of characteristics that is underneath the model. So algorithmic fidelity we've defined as the degree to which the complex patterns of relationships between ideas, attitudes, and sociocultural contexts within a model accurately mirror those within a human population. And we come up with four principles, four criteria that we think need to be met to demonstrate that there is algorithmic fidelity in a language model before using it for research. So the first one is what we call a social science Turing test. This is a little different than a typical Turing test where we're expecting people not to be able to tell the difference between human and generated text. We're looking for sort of a bigger reach. We want GPT-3 to be producing text that is similar in sort of form and function, content, tone, to what we would expect from humans asked to do the same task. The next test is backward continuity. So that means we're generating responses based on a set of backstory. We're feeding it into some content, some characteristics, and we are expecting GPT-3 to give us responses that reflect something about the information that it was given that seems relatively accurate. So that means we could sort of infer back what we know about the content from the responses that it gives us. Forward continuity is the next one. So we expect the generated responses to reflect the form, the tone, the content of the context. So if we are asking GPT-3 to give us answers to a survey question, we need it to give us answers that are the options to the survey question. That's actually a more difficult task than it sounds, but with some work we can get GPT-3 there as well. And the final one is we expect some pattern correspondence. So this means beyond just the surface level, underneath that we expect the responses that it generates to accurately reflect underlying patterns of relationships. So where we see a stronger relationship with some things, we should also see a stronger relationship in GPT-3. Where we see a weak relationship between some ideas or concepts or demographics, we should also see a weak relationship among GPT-3. We don't just want it to see patterns everywhere, we want it to see the patterns that actually exist in the real world. So here's how we go about testing the algorithmic fidelity of GPT-3. We came up with a procedure which is called silicon sampling. And essentially, we are creating a parallel sample of research subjects to what we have in existing survey data. So we're giving some demographic profile background information in the conditioning text. We're having GPT-3 complete the same tasks. So they're answering the same survey questions or doing the same tasks as humans who took the original surveys. one important caveat here is that we have to assess correspondence at the aggregate level, not the individual level. This is not an individual level prediction of a response. It is an aggregate group level prediction of a response. There are lots of statistical reasons for that, but essentially if we're looking at something that is a 60-40 probability and GPT-3 is randomly sampling from that probability distribution, we might end up with a lot of matching or very little matching in ways that don't actually, at the individual level, in ways that would look misleading, even though we have the right distribution in the aggregate. So this is a stochastic sampling process, and so because of that, we sort of do this in aggregate distributions, not individual level results. So our first study is pigeonholing partisans. So we're replicating some experimental data. And what the researchers did in the original project on this is they conducted a survey where they had people write 4 words that describe Republicans and 4 words that describe Democrats. And then they look at whether people who do Republicans use different words to describe Democrats than Democrats use to describe themselves, and they're comparing all of these combinations to see what's going on, what stereotypes do we have of people in the opposite party, people who are not like us. So the task that they were given that humans were given was write 4 words that describe Republicans or Democrats. And we gave the same task to GPT-3. So the backstories would look something like this. Ideologically, I describe myself as conservative. Politically, I'm a strong Republican. Racially, I'm white. I'm male. Financially, I'm upper class. In terms of my age, I'm young. When I'm asked to write down 4 words that typically describe the people who support the Democratic Party, I respond with. And then the text in blue is what GPT-3 filled in for the answer to that. So GPT-3, given this background as a relatively conservative person, says that Democrats are liberal, socialist, communist, and atheist. You can see some of the other completions there. GPT-3, like human contributors, sometimes refused to respond, and sometimes responded in ways that didn't fit the form of the task, which also some people did. Sometimes they would write short phrases or small sentences. GPT-3 does some of this too. Instead of 4 words, it says people who believe in God, people who believe in small government, right? It does some of this. It's sort of non-compliant at about the same levels we found that humans were non-compliant on surveys. So this is what we're asking GPT-3 to do. We're sort of replicating this experiment and saying, can GPT-3, does it understand stereotypes about out parties in a way that if we tell it you're a conservative, does it give us some stereotypes about liberals? If we tell it it's liberal, does it give us stereotypes about conservatives? And we create one of these backstories that exactly matches the demographic information of one of the study participants. So we're just replicating exactly the sample we have in our survey population based on their survey demographic background with GPT-3. Oh, there we go. We'll come back to what it shows a little out of order. So what we find is that GPT-3 and humans use really similar words. There are a set of words, larger bubbles mean the word was used more often. There are a set of words that they use for liberals that they don't use for conservatives, both GPT-3 and humans. They're using essentially the same sort of top words, and the opposite is true. On the other side, they're using the same words to describe Republicans, which are different words than what they're using to describe liberals, or to describe Democrats. We find that GPT-3 mirrors human tone and content. So in this first graph in panel B there, the very first set of bars is a true Turing test. We ask people to guess whether the set of words, we went back to a set of lucid respondents and had them do some coding for us of the responses. And in part of that coding task, we gave them a set of 10 statements, 10 sets of 4 words, and we said, was this written by a human or was this written by a computer? And they guessed in both of them, better than chance, that it was written by a human. They're not, regardless of whether it was actually written by human or by a GPT-3, people tended to assume that they were written by humans at roughly the same level. So people are not passing this Turing test. They can't tell the difference. They can't distinguish between the things that are human generated and computer generated. For the rest of this, we had them code some features of the text that came out in the original research as being part of the differences in how, or part of the characteristics of the kinds of words people use to describe their own party and out parties and some of the differences they found across partisan lines. And so we had lucid coders, again, code for each of these words. How positive was it? How extreme was it? Does it mention some kind of personal trait? Does it mention a particular political issue? Does it mention a group? And in general, they say about the same proportion of GPT-3 text and human text is using each of those tones and each of those forms of content. So GPT-3 is really producing something that is basically the same as what we got out of human respondents on those metrics. In panel A there, it shows positive texts about Republicans are very common among people who are extremely conservative. They become much more negative when we're talking about it, when it's extremely liberal people describing Republicans. Those patterns match across what's happening in GPT-3, what's happening in human text in the ways that you would expect. Right? People have positivity and extremity about their in parties and out parties in ways that we can sort of infer back from what they're talking about. So this sort of shows our human evaluators could not tell which set of words were created by a computer. The tone, the content are pretty similar. It gives us that backward compatibility piece of our text, that humans can reliably infer the partisanship of GPT-3 from the human-generated words. That's one of the tasks we had them do, is the person who wrote this text a Republican or a Democrat, and they were pretty good at figuring that out backwards. The big takeaway here, though, is that conducting the experiment on GPT-3 instead of with humans would have led researchers to the same basic conclusion about partisanship. Right? So they did a whole study using real humans and came to a set of substantive conclusions about partisanship and stereotypes in the United States. Had we just generated the data with GPT-3, they would have come up with basically the same conclusions. That should scare you a little bit. It does us. But we also think it's useful if used appropriately. We're going to run quickly through two more studies that we do to demonstrate this. So the first one is the American National Election Study. We're replicating the data. We're using the same silicon sampling technique. So we're writing up some kind of backstory. We're giving it to GPT-3. And we're just asking, who did you vote for in the presidential election in 2020? Or not in 2020, in 2012, 2016, and 2020. That's notable because GPT-3 finished training in 2019. So it doesn't actually, none of its training data actually knows what happened in 2020, and 2012 is sort of a while back. So we're looking a little bit at the temporal dimension. How well does GPT-3 do across time? There's a whole bunch of numbers in this table which you don't need to read. What you need to notice is that a lot of them are really, really high. So by a bunch of different metrics and using a lot of different demographic backgrounds, GPT-3 gets distributions of who's likely to vote for Republican and Democratic candidates across a set of elections. Right? So it's very good at predicting who's voting or what demographic profiles are voting for different kinds of candidates. This shows us that we can sort of reproduce aggregate correlations between demographics and vote choice, and that we don't have really confining temporal boundaries around GPT-3's knowledge, at least of elections and partisanship. In other places where things change more radically from year to year, you would need to reevaluate the algorithmic fidelity in those settings. Our last study, we're looking at just how fine-grained is algorithmic fidelity in GPT-3. So that was just a very top level. It's an easy answer, right? We say these are the candidates. Actually, we don't even have to tell it. We have to tell it who the candidates are in 2020, but because it didn't know that already from the training data. But in 2012 and 2016, we just asked, who did you vote for in this election? And it knows. But there's sort of two really obvious responses to those questions, right? We know it's, Romney or Obama. We know it's Trump or Clinton. And GPT-3 kind of gets that and has that context. So how does it do when we give it sort of more closed-form questions and ask it a bunch of things, and with a much bigger range of relationships? And so in this study, we used a survey-style backstory. So everything underlined is the information from an actual ANES respondent survey responses, which we have filled into the survey-style format. So we have an interview who's asking questions, and we have me saying these things until we get to the very bottom where it's me, and GPT-3 fills in just that last word. And so then we're using it to sort of impute the last piece of data based on maybe 10 or so other background demographics about GPT-3 and what happens when we tell it some new information. So on this chart, we have GPT-3 in the lighter color. We have human responses in the darker color. This is all Kramer's V, which is a metric of how much additional information or how much additional sort of value or leverage do you get by knowing this piece of information over the distribution of the other variable. And so we're looking at sort of these patterns. The important thing to notice here is that in most cases, these are very close to each other. So Kramer's V, when it's high, tells us there is a stronger correlation between these things. Knowing this piece of information gives you more information about the other demographic or attitude characteristic. When Kramer's V is low, that means there's less of a correlation. And GPT-3 is sort of mirroring across a bunch of these things, that up and down value. When the information gives us a lot in the human sample, it also gives us a lot in GPT-3. When it's less important in the human sample, it's less important in GPT-3. So that's how we're getting to that last piece of algorithmic fidelity. Some important things from this study: it shows us that GPT-3 can be conditioned to answer a variety of survey questions. GPT-3 wants to talk. That's what it's trained to do. So constraining it to a specific set of predefined responses can be a little tricky. But this is a format that seemed to work to get us there. It mirrors a lot of patterns that go beyond the surface level. We're looking at a lot of demographics, a lot of attitudes that go beyond just demographic correlations for vote choice. It's understanding a lot of relationships about what's going on in the world. A few concluding thoughts, and then I'll give you some extensions. The first one is that high algorithmic fidelity is absolutely necessary if we're going to use language models as human simulators. And we should not assume that algorithmic fidelity transfers from one large language model to another, or from one domain of understanding to another. So what we've showed is sort of for American partisanship and election voting behavior, GPT-3 seems to have a pretty good degree of algorithmic fidelity. It understands stereotypes, it understands attitudes, it understands voting behavior, it understands relationships between demographics for that domain. If we're going to use this in any other domain, we would need to repeat a similar set of tests. It doesn't have to be exactly these. It will depend on the particular data that you have, what the right metrics are to evaluate this, but there needs to be very convincing evidence that GPT-3 really understands what's happening in that domain. GPT-3 does appear to have it for this domain of partisanship and public opinion. And so it generates responses that are matching human samples and the patterns that are underneath those responses. The sort of final big conclusion is that we have this one large language model, which is big, but it's not just one distribution or not just one bias that exists. It can produce a whole array of probability distributions that can match different demographic backgrounds based on different conditioning text. And so we can elicit a lot of what GPT-3 knows about a lot of different settings by just changing the input text that we're giving to GPT-3. This allows us to generate silicon samples, which we think is a really exciting way to move research forward by using GPT-3, not just to tell us one thing about the world, but to replicate a whole range of demographic backgrounds. Where do we go from here? Some things our lab is working on, and some other things that we're really excited about and that I hope some of the rest of you will pick up and continue to move forward with in large language models. One thing we're working on is coding open text data. Can we give GPT-3 a code book that normally you would have to give to humans and see if it can classify responses in a meaningful way? We've been talking about data imputation, particularly for open-ended responses. We currently have no technique for imputing data for open-ended responses, but even for survey responses, this may be a way to do effective data imputation. I will put some questions and caveats there. Don't jump in and do it quite yet. It will need a little bit more testing, in particular because of what we said about aggregate level correspondence and distribution seem to be good. Individual level correspondence is a lot. You're dealing with probabilities, and it will depend on how determinative that relationship is. Hard to model or hard to reach populations. So if GPT-3 has information, you need to demonstrate that it has information necessary to model or give us information about a hard to reach population. But if it does, that might give us a way to include more minority or other hard to reach populations into our data modeling. We're really excited about the possibility of using GPT-3 to generate or pilot experimental treatments. So getting GPT-3 to tell us what kind of text to use in a question, or piloting an experiment on GPT-3 first, or piloting several experimental treatments. It's very low cost. You don't have to deal with any people. It's not entirely free. Some models more so than others. There is a paywall for GPT-3 in particular. But it's still very low cost relative to getting actual human participants, and especially given some of the problems that we're facing with survey responses and the use of bots or poor quality data out of survey responses. This might be a way to get around some of that and rely less on human responses if we can have a high quality substitute for some of that piloting data before we then spend more money into higher quality human samples. It also may be valuable in unethical situations where the kinds of questions we would want to ask people or the experiences or the context of the population makes it very difficult to talk with them. GPT-3 may give us some information in those settings. We're also working on designing some experiments where GPT-3 is interacting with humans in experimental settings. So this is one that I'm particularly excited about. A little preview of our upcoming work, which hopefully will be in the field over the course of the summer, is using GPT-3 or another language model as a depolarizing chat assistant. So if we have people have conversations about politics, can we give GPT-3 a set of parameters of this is what a better conversation looks like so that it can then intervene and give us other options. So this is just a little screenshot of what our chat assistant looks like, and the idea is that people will put in a message and then we'll pop up with some alternatives. The GPT-3 will give people other ways of saying things based on a set of principles about what makes a good conversation. And ideally, we can test a variety of those kinds of principles and see what really works well in conversations to improve the quality of our discourse. All right, we'll wrap up there. Thanks for listening, and I hope by now you've been able to understand a little bit more about the possibilities, the excitement, the potential of large language models for social science research, and also some of the reasons why we should be cautious and move slowly as we apply these models in new areas.